type and p-type polysilicon, diode type, single crystal and polycrystalline p-n junction, thermal capacitor type, bimaterial film, and thermistor type, vanadium oxide, amorphous silicon, etc. Photoelectric infrared sensors are mainly used for motion detection, which is difficult to achieve body temperature measurement because this sensor measures dynamic temperature difference. The reactor measures the static temperature difference. In other words, for a photoelectric sensor, when a human body appears and stops in front of it, the charge induced on the surface of the photoelectric element will gradually disappear. Therefore, the human body temperature measured by a photoelectric sensor cannot be accurately captured. The photoelectric effect, well, this is analogous to the piezoelectric effect, but instead of change in a stress displacing electric charge, now it refers to change in temperature causing change in spontaneous polarization and resulting change in electric charge. When the change in temperature delta is uniform throughout the material, the photoelectric effect can be described by means of the photoelectric coefficient, which is a vector p with the equation that the capital P equal to lowercase delta t, where capital P is the spontaneous polarization. This effect is mainly used for thermal radiation detection at ambient temperature. Two metallic electrodes are deposited on faces perpendicular to the direction of the polarization, which yields to a capacitor, acting as thermal sensor. When the detector absorbs radiation, its temperature and hence its polarization changes, thus resulting in a surface charge on the capacitor plates. As for other radiation detectors, photoelectric sensors are also sensitive to thermal noise. The noise equivalent power, NEP, is equivalent input power yielding an output response that in a given bandwidth equals that of thermal fluctuations in the detector. Photoelectric materials. Given that photoelectricity, like piezoelectricity, is also based on crystal anisotropy, many of the piezoelectric materials are also pyroelectric. 10 of the 21 non-centrosymmetrical crystallographic classes have a polar axis of symmetry. All of them display photoelectric properties. There are two groups of photoelectric materials, linear and ferroelectric. The polarization of linear materials cannot be changed by inverting the electric field. This group includes materials such as tourmaline, lithium sulfate, cadmium, and selenium sulfides. Some ferroelectric materials with photoelectric properties are lithium tantalate, strontium, and barium niobate, lead zirconate, titanate, and triglyceride sulfate. Radiation laws, Planck, Wien, and Stefan Boltzmann. We can measure the surface temperature of a heated target by allowing its emitted radiation to be absorbed by a photoelectric detector, which increases its temperature. Thermocouples, thermopipes, thermistors, RTDs, and photoconductors also suit non-contact temperature measurement. Any body at a temperature greater than 0 K radiates an amount of electromagnetic energy that depends on its temperature and physical properties. At temperatures above 500 degrees, the emitted radiation is visible. Below 500, including ambient temperatures, infrared radiation predominates so that only heat energy is perceived. In order to study the emission of energy radiating from a body, we consider first its absorption. Of the overall energy received by a body, part is reflected, part is diffused in all directions, part is absorbed, and part is transmitted, goes through the body. We give the name black body to a theoretical body that absorbs all the energy incident on it, thereby increasing its temperature. A closed cavity with black walls and controlled temperature and where only a small aperture is provided, behaves approximately as a black body. At any temperature, our bodies emit radiation and absorb that coming from other bodies in their environment. If our bodies are not at the same temperature, the hotter ones will cool and the colder ones will heat. So radiation is enough to reach thermal equilibrium. Heat conduction and convection are not required. When equilibrium is reached, all bodies emit as much radiation as they receive. Therefore, the bodies emitting more radiation are those that also absorb more, and hence a black body is also the best radiation emitter. Heat sinks are black. Greenhouses rely on materials that are transparent to visible light but opaque to infrared radiation emitted by bodies heated by that incident light. When this radiation arrives at an object, part of it is absorbed. When the absorption is high, the increase in temperature of the object can be significant. This is the principle of operation for thermal detectors, thermopiles, and bolometers, RTD, thermistors, and photoelectric detectors. In contrast, quantum detectors, photoconductors, photovoltaic detectors are based on the generation of electrons by incident photons, which results in a change in resistance or the contact voltage of a p-n junction. In practice, the presence of water vapor, carbon monoxide, and ozone in the air, the dispersion due to dust particles, smoke, and so on results in a decrease between the radiation emitted and that detected. In addition, the emissivity of the target may be unknown or may be changed because of varying surface conditions. Two color or radio pyrometers solve these problems by measuring two different wavelengths emitted by the target. If those wavelengths are close enough to undergo the same undesired variations, the radio between the signals outputs changes only when the temperature changes at the target. The two signals needed can be obtained by a beam splitting mirror and match detectors or by a filter wheel and a single detector. Applications. The most common application for the photoelectric effect is the detection of thermal radiation at ambient temperature. It has been applied to perometers, non-contact temperature methods in furnaces, melted glass, or metal films, and heat loss assessment in buildings. In radiometers, measurement of power generated by a radiation source. Other applications are IR analyzers based on the strong absorption of IR by carbon monoxide and other gases, intruder and position detection, automatic faucet control, fire detection, high power laser pulse detection, and high resolution thermometer. Medical thermometers that measure the ear temperature detect infrared radiation from the eardrum and surrounding tissue. Undesirable parasitic changes may neutralize the surface charge induced in the electrodes by desired temperature changes in the detector due to the incident radiation. Thus, the incident radiation must be modulated, usually by a low-frequency optical chopper that alternatively faces the detector to radiation from the target and from an object at ambient temperature. A coherent detector synchronous with the chopper eliminates ambient noise. An alternative technique to reduce bulk or common mode effects uses dual-element series opposed detectors. Photoelectric sensors are faster than other thermal detectors, thermocouples, thermistors, because they are thin, have high sensitivity, and do not need to reach thermal equilibrium with the radiation source because they detect temperature gradients. This makes them appropriate for imaging by scanning the surface to be detected as used in infrared thermography.